Okay, so we got major head loss, which is what we're looking at right now. So head loss is when you lose energy out of water. Friction and turbulence cause it. It occurs in flowing water only. Okay, major head loss occurs in pipes. Minor head loss occurs in fittings. All right, so head loss depends on how rough the pipe is, how long the pipe is, and how fast the water's moving. Keep in mind that fast water velocity or high water velocity can be caused by a high flow rate or a low pipe size or a combination of both. Okay, now head loss is independent of pressure. It doesn't depend on that. There's two methods. They're both created around the early 1900s. Hayes and Williams, which is easier but less accurate, and then Darcy Weisbach, which is harder but more accurate. Darcy Weisbach is more theoretically derived. So there's the Darcy Weisbach formula there. Head loss is v squared over 2g, which is velocity head, times the length divided by the pipe diameter times a friction factor, which describes the roughness of the pipe. The hardest number to get in this formula is the friction factor. Okay. So to find F, you concern yourself with a few things. The first thing is a Reynolds number, which will help us figure out whether the flow is a laminar, which means nice and smooth and linear, or if it's turbulent, which means it's kind of, well, turbulent. It's got a lot of motion and it's going all different directions as it moves through a pipe. So the Reynolds number is the first number we have to figure out. That's the pipe diameter in feet. Keep that in mind. Velocity in feet per second, density of the fluid, divided by the absolute viscosity. Okay, so the first thing we want to do here is find F. Okay, now we can get that off of a chart. To get that, we need to get the relative roughness, which is the depth of the largest imperfection in feet in the pipe, divided by the diameter of the pipe, again in feet. Then you find F on your pipe, or on the chart there. Okay. We might need to interpolate a little bit off of this chart to get F. So what we're going to use to get F is the Reynolds number from down here, and then the epsilon over D ratio. Epsilon's the average imperfection in the interior of the pipe, D is the diameter of the pipe. That's a ratio. Okay, so we need both of those things to get our friction factor. So we're working through an example here, 600 gallons per minute, 1,800 feet of pipe, 6-inch unlined cast iron, 70-degree temperature. So we went on page 58, I think it was, and we found the absolute viscosity and the density in slug per cubic foot. No, I think it's slug, those units aren't quite right. Yeah, density is just slug per cubic foot. Okay. So that second in there shouldn't be there. I don't think you've got it in yours. Okay. So we looked it up for 70 degrees. You might have a little typo in your book that said 60. It's actually 70. So we got 0.0000203 pounds second per foot squared and 1.936 slug per cubic foot. Okay. And then we threw all that into this Reynolds number, and we figured out the Reynolds number was about 325 times 10 to the 5, just by plugging everything in. So the Reynolds number is the diameter of the pipe in feet. 6-inch pipe is a half-foot diameter. 6.81 feet per second for the velocity. Density is 1.936 slug per cubic foot, and then viscosity is 0.0000203. Okay. Now, I was mentioning that the place to find velocity now, instead of doing a bunch of calculations, is on this chart right here. This is the Hayes and Williams chart. Okay. So that's good if for nothing else to find velocities. That's on page 108.
Correct.
108. So we got 6-inch pipe. And so what we've got going on here is 6-inch pipe, 600 gallons per minute. So if you have a look on the chart, 6-inch pipe. At that flow rate, that gets us right about there. And what you're going to see is you've got a velocity of 6.81 feet per second. Okay, everybody finding that okay? So that chart is handy. If you got regular pipe sizes and regular flows, you can find velocities right off of it. So that's not all bad. You don't have to go through all the whole V equals Q over A thing. You can just find it right off the chart. All right. So that's the Reynolds number. So that's one thing we need to have to find F. The other thing we got to look at is the pipe itself. We've got unlined cast iron. Now that's the pipe back from 100 years ago, which you still find in the ground. Okay, would be unlined cast iron. Nowadays they use what? Lined ductile iron, right? Where they put a mortar lining in there, and the iron's ductile, so it doesn't shatter quite as bad if you hit it or something like that. But so we're using unlined cast iron. So it looks like our relative roughness epsilon is 0.0008. Now that's off of that Moody diagram, is where I'm getting that. And there's just a little bit of an inset in there that has some of those numbers. So that's on page 120. Unlined cast iron, 0.0008. Okay. Now keep in mind that's in feet. So we've got 6-inch pipe, which equals 0.5 feet. So if we want epsilon over D, what we get is 0.3 zeros and an 8 divided by 1/2. So epsilon over D is dimensionless because you just get feet over feet. It's just a ratio. So that'll be 0.0016 is what that'll be. All right, so there you go. So now we're ready to go to the Moody diagram, all right? So we got what? 325 times 10 to the 5th. So that's down here. That's about like that. Draw straight up. And then we've got a epsilon over D is 0.0016, I think. And here's 0.0020, and there's 0.0010. So I think we're a little ways between the two. So what we're going to do is kind of just run that curved line until we intersect the vertical line we've got.
Thank you.
Yeah, so 0.0016, so there we go. And then we just kind of go down the middle right about there. Am I okay with that? 0.0020, 0.0010, right? So we're in between those two. And then from there, we take that line over like so. And we get something on the order of 0.023 for a friction factor. Okay, so we drew a vertical line up at the Reynolds number. We found our 0.0016 value. We interpolated it here, and then we followed those curved lines in and intersected the vertical line. Then we hung a straight left and got over there to the friction factor, 0.023. You doing okay with that? We're good? Okay. Good. All right. So now we just plug everything in, okay? And this says velocity. It should say head loss. So let's find the head loss. We just plug everything in and run the numbers and see what we get. So the head loss is F, which is 0.023, times the length of the pipe. How long is that? Is it 1,800 feet? Okay, thanks. Great, 1,800. What is it, V? Is it 6.81 or something? 6.81 feet per second. We square that. And then we divide that by the diameter of the pipe. You got to remember to keep that in feet, though. So that's half a foot. 2 is 2. G is 32.2 feet per second squared. There we go. And then we run the numbers, and we'll get the head loss for that run of pipe. And I'm getting about 59.6 feet. So there you go. That's how that's done. And most of the work went into getting that number right there. So that's one way to find head loss. I think it's generally considered to be the most accurate way, but it's also a fair amount of work to get it done. Okay. You'll find this on computer programs and things like that, you know, this method. Yeah, I think you could, if you got it on software, this is generally how I think it would work. Okay. But you know, the one thing I keep in mind with this stuff is, you know, actually calculating a true head loss for a pipe that's got, who knows what's in there, you know. Yeah, right. You got an idea. What you're getting out of this is an idea, and you use it, and everybody uses these methods, and they work fine. And you know, we design stuff that works properly, so the method's all good. But you know, I'm not going to say it's exactly that. I mean, it can be a good bit different, really. Exactly. Yeah. Right. Yeah. That's how that would go. Right. Okay. Now, one problem is, again, that's a bit of work. Okay. So luckily, there were a couple other people working on this at the same time, and they were Hazen and Williams, and they came up with this crazy-looking formula here. Which, notice, the Darcy Weisbach has some logic to it. You know, it's FL over V squared over 2G and then divided by D. Everything's kind of simple and makes sense here. Hazen Williams just got a bunch of data, plotted it up, and came up with this formula. Yeah, where we at?
Is this in our...
Yeah, we got to go backwards. So we're on about page 107, is it?
Okay. Found it.
We good? I don't know what page it's on.
Yeah, it's 107. It is 107.
107. Okay, great. All right, so this now, that doesn't look like a very simple formula, and it's not. You know, and you can see what all you get out of this. You've got head loss, you got flow in gallons per minute now, you got C, which is the roughness coefficient, and you got the diameter in inches. And what they've got there is head loss is 147.85 times the flow rate divided by the roughness factor, divided by the diameter of the pipe in inches to the 2.63 power, and you take it all to the 1.85 power. Yeah, no, they just plotted up a bunch of data, I think, and did a best fit kind of curve relationship is what they did. And it's kind of a crazy equation, obviously. So the equation isn't that much easier to run, although actually it's not bad because you can get C pretty quick. You could program this in your calculator if you wanted. But why should we even bother with that? Because it's shown in a chart, okay? So someone has done all this for you. Namely me, about 15 years ago. But you can find this stuff on the internet too. Okay, so what you get on this chart is head loss in feet per 100 feet. So this will tell you how much head loss you've got per 100 feet of pipe. It'll also tell you the velocity in feet per second, which I've mentioned, which is, good. This is for C equals 100. Okay, so you have different C values for different pipes. This particular chart is for C100, and it's hard to find charts for C other than 100 for some reason. The pipe size is the inner diameter. All right. So I don't know, why don't we just have a look here. Let's just Google that and see what we come up with.
What happens if it suddenly goes 200? Can you just double it here, or does it become...
That's a good question. So the question is, what happens if your C is not 100? And you can adjust for it. So let's use it, okay, and see what we can do with it. So this chart, I've kind of told you what it's for. C100 gives head loss in feet per 100 feet, okay? So let's find the head loss per 100 foot for 400 gallons per minute flowing in a 6-inch pipe. So 400 gallons per minute flowing in a 6-inch pipe. And I'm on page 109.
Yeah.
Is it what?
2.2.
Yeah, 2.2. Y'all finding that okay? It's just right on the chart, so it's no big deal. Y'all good? 2.2 feet per 100? Just watch the chart. Be sure you're in the proper column, because the other one's for head loss, the other's for velocity. Okay, so we're 100 feet, 400 gallons per minute, 6-inch pipe, right? So let's try this thing out here, see if it works. So 100 feet, C was 100, right? Q was that 400?
400.
400. Inside hydraulic diameter in inches. Oh, okay. And was it 4 inch or 6? 6. Okay. 6. Calculate.
4.54. Oh, that's lost.
Head loss is, yeah, it's pretty good. 2.224. 2.25. We got what? 2.29 or 2? What did we get?
2.20.
2.20. Okay. I think we can live with that. Yeah. All right. Okay. So there you go.
That's for H2O.
Yeah. These charts are for water. I've never really looked at head loss in other fluids. I guess they would be different depending on their viscosity and all that. Yeah. So this is just for water under average conditions. Okay, it also has the velocity at 4.54. Is that looking about right?
Yep.
Okay. So there you go. All right. Now let's say instead of being 100 feet, it's 300 feet. So what would you do to your 2.20, do you suppose? Yeah, okay, so we got 2.20. Now that's feet per 100 feet. But we got 300 feet. See, that what comes off that chart is the head loss per 100. We got 300 feet though. So you just have to factor it up, okay? So what I do, I just take 2.20 feet, and then I say I've got 300-foot lengths is what I do. 6.60 feet. Okay. So I just take the 100 out of the length, because the head loss off that chart is per 100 feet. You okay with that? You just factor it up by the length. That's about all there is to it.
Nice and simple. At least it's not doing a squaring itself and everything else.
Yeah, right. It's just a chart. It's pretty straight up, which is why people like to use it. But the price you pay on this is accuracy a bit. That's the problem with it. Okay, why don't you just do the next 3 then? Just work them out. getting 2.29 for the first one. You doing okay with that? Yeah, it is. 2.98. And then 83.7. Okay. So what we got? 600. Let's try that internet thing just one more time, try and get a little bit of a range. Now what I found was this, according to the charts anyway, the formula breaks down a little bit for low flows in small pipes. So there was some inaccuracy in it on the straight formula is what I found. So what, 600 gallons per minute, 1,800 feet, 6-inch pipe. So CL was 1,800 this time. 600 gallons per minute, 6-inch pipe, calculate. Actual head loss 85.7, okay, versus 83.7, no big deal, that's good. Right now, there's a little bit of a problem with this chart though, and that is it's locked in for C100. So on page 110, we address that because modern pipes are no longer C100. C100 was the standard back when these, when Hazen and Williams were developing this, but it's not anymore. Nowadays we have pipes up around C140 or C150. Okay, so the higher the C, the smoother the pipe. Nowadays the common water pipes that we use this for are what? What are the two common water pipes currently that go in the ground? PVC. Yeah, PVC C900, that light blue, thick walled stuff, and then ductile iron pipe with a mortar lining. The ductile iron's about C140 when it's new. The PVC is C140 or even 150. So C isn't 100 anymore. But the charts for C not equal to 100, they're not generally available, although we got this nice little thing on the internet here, but we'll test this again. So what we got to do here to account for that, if C is not 100, which quite often it isn't these days, is find what we call an equivalent flow. So you take the actual flow times 100 over whatever your C is. Then instead of using the actual flow, you use an equivalent flow on the tables. So that's how that works. Okay. So as an example of this, let's find the head loss for 480 gallons per minute. Or let's see, what have I got? I've got 480 gallons per minute flowing through 250 feet of 8-inch pipe, C120, okay? So instead of, now what you do for C120, that's going to be smoother pipe. The higher the C, the smoother the pipe. So that's smoother pipe than C100. So that means you're going to have less head loss. So what you do is you find the equivalent flow. Okay. Now what that is the actual times 100 over C. So we're going to find the equivalent flow, which is the actual, which is 480 gallons per minute, times 100 over C. Now C is 120. So when you multiply that, you get 400 gallons per minute. Now notice what's happening here is this is a lower flow, isn't it? So Q equivalent is lower than Q actual. So there's less head loss in this case also. So this is how you handle it when you've got a smoother or rougher pipe than C100. You convert the flow.
So what's actually coming out of the pipe is your Q actual, right?
Right.
Okay.
That's actually what's coming out of the pipe. If you want to find the velocity, use Q actual, because you're putting a certain amount of flow through a certain size hole, you get a certain you know, a certain velocity out of that, but this will get you the head loss. So you use a lower flow. Okay, so if we find 400 gallons per minute, and we've got now use C100 for this calculation because we're using the lower flow, not the actual flow, but the lower flow, an 8-inch pipe. What do we got for head loss now? Is it? Okay. Okay. So 0.54 feet per 100 feet. Okay. Yeah, right. So we got feet, 0.54 feet per 100 feet. So you take the 0.54 feet and you multiply it up by 2.5 because you got 2.5 100-foot lengths. And you'll get the actual head loss for the system out of that. It's 1.35. So that's how you handle that, okay? You all good with that? So you got this extra step where you have to find the equivalent flow.
Can you do this when you only have a chart that's C100?
Right. So yeah, you do this if you got a chart that's C100. Now, I don't know, let me try this thing out again. So 250 feet. C120. 480, yeah, you'd use the actual flow here. And then inside diameter in inches is 8. 8. Calculate.
Yeah, 1.38, 1.25.
Yeah, okay. This thing's coming just a little bit higher than what we're getting. It's fine.
It's probably good, right?
Yeah, right. Yeah, generally. Now, yeah, generally speaking, you know, it's okay to come in a little high. You want to be a little careful on that if you're doing pumping systems, because you don't want to over-design a pump too bad, because you can cavitate and do some things. That you want a pump that fits your system. You don't want to oversize it too much. But, you know, this is plenty good, so far anyway. Well, try and get the pump about right. I'll oversize it a little bit is what I'll do, because I'll figure as the system ages, it'll have to push against more head loss. But I don't want to I want to.
Goldilocks.
Yeah, right. Yeah, you don't want to really, you know, sometimes inclination is I'll just put a really huge pump in there, but that may not work well, you know, depending on what you're trying to do. Okay. So why don't you guys do the one on page 111. So that's older pipe, so C's 80. So I think of that as maybe being pipe that's corroded or has some other problems. 106.60. Thereabouts. Okay. So that's how you can adjust that chart when your C is not 100. Okay, what do we, so we good with that? Just using this thing and working this stuff out. Okay, how about going to page 121 again? If we got, what do we got on page 121? If we were to convert this into Hayes and Williams, we did that with the Darcy Weisbach. Let's do it with Hayes and Williams. This is the same thing. So what we've got there for that problem is what? We've got 600 gallons per minute flowing through 1,800 feet of 6-inch unlined cast iron. Oops. Yeah, okay. So 600 gallons per minute.
4.65.
Now, unlined cast iron, what's the C value for unlined cast iron? When it's brand new. It's 100. That's what they based it on. But that's when it's new, which, you know, yeah, we'll see. You know, we'll just see how that plays out. So we'll just go with that. 600 gallons per minute, 6-inch pipe. What are we going to get for head loss if we do that? Did we do this? I don't know if we did this already. I don't think we did. Is it 4.65?
Yeah.
Lose some. So we get 4.65 feet. And then 18 100-foot lengths. And then we get, what, 83.7?